Welcome back to another deep dive into the OEIS,
Yeah.
the online encyclopedia of integer sequences. For those of you who are new to the OEIS, it's a vast collection of integer sequences, and it's like a treasure trove for mathematicians. Especially those of us interested in number theory. Today we're going to be looking at a particularly interesting sequence, OEIS sequence A000158.
Right. And this one is particularly interesting because it has some unexpected connections to statistical mechanics.
Oh, very cool. So maybe just start off, can you give us like a brief overview of what this sequence A000158 is all about?
Sure. So A000158 deals with something called partitions into non-integral powers. Now, that might sound a little bit intimidating at first, but let's break it down.
Okay.
So first, let's remind ourselves what a partition is in the context of number theory.
Yeah, so a partition of a positive integer. It's just a way of writing that integer as a sum of smaller positive integers.
Exactly. So, for example, the number 4 has 5 partitions. You can write it as 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 2, or 1 plus 3, or 2 plus 2, or just 4 itself.
Right, right. So essentially we're just breaking down a number into its additive components.
Exactly.
Okay.
Now, the non-integral powers part, that's where things get a little bit more unusual.
Yeah, what exactly do we mean by non-integral powers?
So, non-integral powers refer to exponents that are fractions,
Okay.
like 2/3 or 1/2. So instead of dealing with whole number exponents, we're now working with exponents that are rational numbers.
Okay, so it's like taking the concept of partitions and then adding this extra layer of complexity by introducing these fractional exponents.
Precisely.
Right.
And to make this a little bit more concrete, the OEIS entry for A000158 actually gives us a helpful inequality.
Okay.
It says that the nth term in the sequence A of n corresponds to the number of solutions to this inequality. x1 to the 2/3 plus x2 to the 2/3 plus x3 to the 2/3 is less than or equal to n,
Okay.
where x1, x2, and x3 are integers.
All right, so let's break down this inequality.
Sure.
It seems to provide a more concrete way of understanding what this sequence is counting.
Exactly. So what this inequality is saying is we're looking for sets of 3 integers, each raised to the power of 2/3, and their sum has to be less than or equal to n.
Okay.
And the sequence counts how many of these sets exist for each value of n.
So for example, if n is 5, the sequence would tell us how many different combinations of 3 integers raised to the 2/3 power would add up to something less than or equal to 5.
That's right.
Okay. And now, I know you mentioned earlier that this sequence has some connection to statistical mechanics.
Yeah.
And that's the part that I'm particularly curious about because, as I recall, statistical mechanics deals with the behavior of systems with many particles, like, gases or liquids.
Right.
How does that connect to this sequence of numbers?
Well, that's where the beauty of mathematics often lies, in these unexpected connections between seemingly disparate fields. And there's a paper from 1951 by Agarwala and Alok titled Statistical Mechanics and Partitions into Non-Integral Powers of Integers that explores this very connection.
So they found a way to relate this very abstract number theory problem to a physical system.
Yes, exactly.
That's fascinating.
Their paper uses the principles of statistical mechanics to analyze this particular partition problem.
Okay.
And they do this by establishing a correspondence between the terms in a partition and the energy levels of particles in a system.
Oh, okay. Can you elaborate a bit on that correspondence?
Yeah, sure. So imagine you have a system of particles,
Okay.
and each particle can occupy certain discrete energy levels.
Right.
Now think of each term in a partition, like x1 to the 2/3, as representing one of those energy levels.
Okay, so instead of thinking about just abstract numbers being added together, we're now picturing these particles occupying specific energy levels within a physical system.
Exactly.
Got it.
And by applying the tools of statistical mechanics, which deal with the distribution of particles among different energy levels, they could then analyze how these partitions behave.
So it's like they're translating a number theory problem into the language of physics.
Exactly.
That's really cool. Now, looking at the first two terms of the sequence, we have 1, 2, 8, 19, 41.
Right.
What can we glean from these numbers?
So these numbers represent the number of partitions for the first few values of n. As you can see, the sequence grows rather quickly, and Understanding this growth pattern and deriving formulas to describe it is a key challenge in number theory.
So it's not just about listing the partitions, but about understanding the structure of how this sequence evolves.
Exactly. And to do this, mathematicians use various tools and techniques like generating functions, asymptotic formulas, and they even connect it to other areas of mathematics like combinatorics.
Sounds like a lot more to this sequence than meets the eye.
Absolutely. A seemingly simple concept like partitioning numbers into non-integral powers can lead us down a very interesting rabbit hole of mathematical connections and challenges. And the work of Agarwala and Alok really shows how even seemingly unrelated fields like statistical mechanics can provide powerful insights into number theory problems.
Yeah, this is why I love exploring the OEIS. You never know what you're going to find
Right.
and what kind of unexpected connections you might discover. Now, I'm curious to dig a little deeper into Agarwala and Alok's approach. What specific techniques did they use to bridge the gap between partitions and statistical mechanics?
One of the key tools they used was something called Q-series.
Q-series?
Yeah, which are a special type of generating function. And generating functions are a very powerful way to encode a sequence of numbers into a single function, which allows us to analyze the sequence much more effectively.
So they essentially took Agar000158 and compressed all its information into a single function using these Q-series.
Exactly.
And then by manipulating these Q-series, they were able to derive asymptotic formulas that describe the behavior of the sequence as n gets very large.
That's right.
So they could kind of predict how the number of partitions grows as we consider larger and larger values of n.
Precisely. And their work really paved the way for a lot of further research into these connections between partitions and statistical mechanics, leading to new discoveries and a deeper understanding of both fields.
Very cool.
Yeah.
All right, so now I'm kind of curious about these visualizations that they use to represent these partitions. I noticed that their paper included some tables and graphs. Can you tell us a little bit more about what kind of information they presented through these visuals?
Yeah, sure. So the tables provided a very systematic way to showcase the number of partitions for different combinations of n, the number being partitioned, and the exponent. So you could see at a glance, for example, how many partitions were possible for n equals 5 or n equals 10 and so on, with the exponent fixed at 2/3.
So they basically created a lookup table where you could easily find the number of partitions for a specific set of parameters.
Exactly.
Okay, but what about the graphs? What insights did those offer?
So the graphs took it a step further by depicting the distribution of these partitions visually. So if you imagine fixing the exponent at 2/3 and then varying inside, the graph would then illustrate how the number of partitions are spread across different configurations as n increases.
So instead of just seeing the total number of partitions, we get a sense of how these partitions are arranged.
Exactly.
Okay.
And what's interesting is that for certain exponents, like the 2/3 we've been focusing on the graph, starts to resemble a bell curve,
Oh, wow.
similar to a normal distribution.
That's a curious observation.
Yeah.
It almost suggests that there might be some underlying statistical principles at play governing how these partitions are distributed. Makes you wonder if there's like a connection to the central limit theorem or something.
Yeah, it's an intriguing thought. And while their paper didn't dive deep into that particular connection, it definitely opens up avenues for further exploration. It highlights how even a simple concept like partitioning numbers can touch upon some very profound mathematical ideas.
Absolutely. All right, well, let's revisit this connection to statistical mechanics one more time. You mentioned earlier that they drew an analogy between the terms in a partition and the energy levels of particles. Can you elaborate on how that analogy actually helped them to apply statistical mechanics to this problem?
Sure. So imagine a system of particles,
Okay.
each of which can exist at specific discrete energy levels.
Right.
Now picture each term in a partition, like x1 to the 2/3, as representing one of those energy levels that a particle can occupy.
So instead of just dealing with these abstract numbers, we're now visualizing this physical system
Exactly.
with particles distributed among different energy levels.
And by applying the principles of statistical mechanics, which govern how particles are distributed among energy levels, they could then analyze the behavior of these partitions, much like they would study the properties of a physical system.
It's remarkable how they kind of transform this number theory problem into something that can be analyzed using the tools of physics.
Right. And what's even more interesting is that they didn't just use one type of statistical mechanics. They explored both Bose-Einstein statistics and Fermi-Dirac statistics, which have different rules for how particles can occupy energy levels.
Oh, yeah. I remember those from my physics courses. Can you remind us about the key distinction between these two types of statistics?
Yeah, so in Bose-Einstein statistics, multiple particles are allowed to occupy the same energy level.
Okay.
Whereas in Fermi-Dirac statistics, each energy level can hold at most one particle.
So it's like having a set of boxes, and in the Bose-Einstein case, you can put as many particles as you want into each box. But in the Fermi-Dirac case, each box can only hold one particle.
Yeah, that's a great analogy. And this difference in how particles occupy energy levels leads to different mathematical formulations for how those particles are distributed.
I see. So how did this difference in statistics actually play out in their analysis of the partition problem?
So by applying both Bose-Einstein and Fermi-Dirac statistics to their model, they were able to derive different expressions for the number of partitions.
Okay.
And this highlighted how the choice of statistics, the rules governing the particle behavior, influence the overall distribution and arrangement of these partitions.
So the seemingly abstract choice of statistical framework has a very concrete impact on the mathematical structure.
It does.
So that's fascinating.
Yeah. It underscores how profoundly intertwined the quantum world and the realm of abstract mathematics can be. It's a reminder that seemingly unrelated areas of study can offer some very unexpected insights and connections.
Absolutely. Now, I'm kind of curious about the specific mathematical tools they use to analyze these partitions. You mentioned earlier something called Q-series. Can you tell us a little bit more about those and how they fit into the picture?
Sure. So Q-series are a special type of generating function. Generating functions essentially provide a way to encode a sequence of numbers into a single function, allowing us to study its properties much more efficiently.
So they essentially took A000158 and encapsulated all its information into these Q-series.
Exactly.
What's so special about Q-series compared to other types of generating functions?
So Q-series involve a variable Q that can represent a complex number, and they exhibit some really remarkable properties that make them particularly useful in number theory and combinatorics. And by manipulating these Q-series, Agarwala and Alok were able to derive asymptotic formulas that describe how the number of partitions behaves as n, the number being partitioned, grows very large.
So they could predict the long-term trends and patterns in the sequence.
Precisely.
Even for values of n, that would be very challenging to calculate directly.
Yeah, and their use of Q-series really highlights the power of generating functions as a tool for understanding the behaviors of sequences.
Okay, let's shift gears a bit and delve into those visualizations again.
Okay.
Those tables and graphs that they created. Can you describe them in a bit more detail? Explain how they enhance their analysis.
Yeah, sure. So their tables very meticulously listed the number of partitions for various combinations of n and the exponent. So imagine a table with rows representing different values of n and columns representing different exponents.
Okay.
Each cell in the table would contain the corresponding number of partitions.
So it's like a comprehensive reference guide where you can quickly find the number of partitions for a specific set of parameters.
Exactly.
What about the graphs? What kind of visual representation did they provide?
So the graphs depicted the distribution of partitions for a fixed exponent as n varied. Imagine a graph with the x-axis representing n and the axis representing the number of partitions. The curve on the graph would then show how the number of partitions changes as n increases.
So it's like a visual snapshot of how these partitions are arranged as we consider larger and larger numbers. Did they observe any interesting patterns or trends from these graphs?
They did. For certain exponents, like the 2/3 we've been discussing, the graph started to resemble a bell-shaped curve similar to a normal distribution.
That's fascinating. It hints at a deeper structure underlying the distribution of these partitions, perhaps even a connection to the central limit theorem, though they didn't explicitly explore that in their paper.
Right. It serves as a reminder that even in a well-defined mathematical problem like this, there are always new avenues to explore and potential connections to uncover.
Now, before we wrap up this deep dive into A000158, I'd like to touch upon the broader impact of Agarwala and Alok's work. Did their findings have any implications beyond this specific sequence? Did it influence other areas of mathematics or even physics?
Absolutely. Their research made significant contributions to the theory of partitions,
Okay.
which is a very vibrant area of number theory with connections to various other branches of mathematics.
Can you give us some examples of those connections?
Sure. So partitions have ties to combinatorics, which deals with counting and arranging objects, and to analysis, which studies functions and their properties. There are even connections to representation theory, which explores how abstract algebraic structures can be represented using matrices and linear transformations.
So their work had this ripple effect across the mathematical landscape,
It did.
influencing the development of these various fields.
Yes, and it also served as an inspiration for further research into the interplay between statistical mechanics and number theory, a connection that might have seemed unlikely at first glance.
It's a testament to the power of interdisciplinary thinking and the unexpected ways in which different fields of study can enrich and inform one another.
Yeah, it's really quite remarkable.
Absolutely. All right, well, unfortunately, we're out of time for today.
Okay. And it's amazing how, even with these abstract concepts, they still had to deal with these very real-world limitations.
It's true. Even back then, computing power was a major constraint.
Yeah. Calculating the number of partitions, especially for large values of n, that was a really daunting task, even with the computational tools they had available at the time.
So how do they manage to overcome that obstacle?
Well, instead of trying to calculate every single partition directly, which would have been incredibly time-consuming, they focused on developing these asymptotic formulas. These formulas allowed them to approximate the number of partitions for large values at n without having to enumerate them all individually.
So like finding a clever shortcut
Exactly.
that lets you estimate the answer without having to do all the heavy lifting. Did they address how accurate these approximations were?
Yeah, they were very thorough in analyzing the error bounds of their asymptotic formulas. They wanted to ensure that their approximations were reliable and could provide meaningful insights.
That's a crucial step in any kind of mathematical research, making sure your results are valid. Now, before we move on, I want to circle back to one of the most fascinating aspects of this sequence, its connection to statistical mechanics. What were some of the key insights that emerged from applying this physics framework to this number theory problem?
Well, their work really revealed this profound interplay between the quantum nature of particles and the way that these partitions are distributed. By treating the terms in a partition as energy levels and applying different statistical models like Bose, Einstein, and Fermi Dirac statistics, they discovered that the specific rules governing particle behavior have a direct impact on the mathematical structure of these partitions.
So even though we're dealing with these abstract mathematical concepts, they're somehow governed by the same principles that dictate how particles behave in the physical world.
It's really quite remarkable, isn't it?
It is. It highlights these deep connections that exist between these seemingly disparate areas of science and mathematics, reminds us that even in a field as abstract as number theory, there can be these unexpected connections to the physical world.
Absolutely.
This has been a truly enlightening exploration of A000158. As we conclude our deep dive, what are some of the key takeaways that you'd like our listeners to remember about this sequence?
I think the most important takeaways are that even seemingly simple mathematical concepts like partitions can lead to surprisingly deep and complex mathematical connections. And second, the work of Agarwala and Alok really demonstrated the power of interdisciplinary thinking, showing how tools and concepts from physics can be used to illuminate problems in number theory.
It's a great reminder that the world of mathematics is full of surprises, and the boundaries between different fields are often more fluid than we might think. Thanks for guiding us through this fascinating deep dive. We encourage all of you to keep exploring the OEIS and see what other mathematical treasures you can uncover. Until next time, happy exploring.
Yeah, it really is. It makes you wonder about all the other hidden connections that might be out there just waiting to be discovered. I imagine that conducting this kind of research back in 1951 presented its own set of challenges, especially when it came to the computational aspects of their work.
Oh, absolutely. Computing power was a huge limitation back then, calculating the number of partitions, especially for large values, and that was a really daunting task, even with the tools they had available.
So even though they were dealing with these abstract concepts, they still ran into these very concrete limitations in terms of computing power. How did they work around that obstacle? Well, they had to be quite resourceful. Instead of trying to calculate every single partition directly, which would have been incredibly time-consuming, they really focused on developing those asymptotic formulas that we talked about earlier. These formulas allowed them to approximate the number of partitions for large pornet without having to go through the process of enumerating them all individually.
It's like finding a shortcut that lets you estimate the answer without having to do all the heavy lifting. Did they happen to mention how accurate these approximations actually were?
Oh, yeah. They were very meticulous about analyzing the error bounds of their asymptotic formulas. They wanted to make sure that their approximations were reliable and could provide meaningful insights into the true behavior of these partitions.
That's a crucial step in any mathematical research, making sure your results are valid and reliable. Now, before we wrap up our deep dive into A000158, I'd like to circle back to one of the most fascinating aspects of this sequence, its connection to statistical mechanics. What were some of the key insights that emerged from applying this physics framework to a number theory problem?
Well, their work really revealed a profound interplay between the quantum nature of particles and the way these partitions are distributed. By treating the terms in a partition as energy levels and applying different statistical models like Bose-Einstein and Fermi-Dirac statistics, they discovered that the specific rules governing particle behavior have a direct impact on the mathematical structure of these partitions.
It's fascinating how, even though we're dealing with these abstract mathematical concepts, they are somehow governed by the same principles that dictate how particles behave in the real physical world.
It really highlights those deep connections that exist between these seemingly disparate areas of science and mathematics.
Hmm.
And it reminds us that even in a field as abstract as number theory, there can be these unexpected connections to the physical world.
This has been a truly enlightening exploration of A000158. As we conclude our deep dive, what are some of the key takeaways you would like our listeners to remember about this sequence?
Well, I think the most important takeaways are, first, that even seemingly simple mathematical concepts like partitions can lead to surprisingly deep and complex mathematical connections. And second, the work of Agarwala and Alok really demonstrated the power of interdisciplinary thinking, showing how tools and concepts from physics can be used to illuminate problems in number theory.
It's a great reminder that the world of mathematics is full of surprises, and that the boundaries between different fields are often more fluid than we might think. Thanks for guiding us through this fascinating deep dive. We encourage all of you to keep exploring the OEIS and see what other mathematical treasures you can uncover. Until next time, happy exploring.